Today we're going to continue to discuss solving systems of linear equations using the elimination method. So let's get started. So we've looked at three ways of solving systems of linear equations. And right now we're talking about the elimination method. Now this is also called elimination by addition. Because with both algebraic methods, the goal is to temporarily eliminate one of the variables. And so with the elimination method, we eliminate by addition. We add the two equations together. Let's take a look at an example from our previous lesson. So the first step to solve this system of equation using elimination is to write both equations in standard form. So the second equation is in standard form, but the first equation is not. So let's rewrite y equal to x minus 11 in standard form. So we have y equal to x minus 11. I'm just rewriting the equation. Then let's get this x to the left side. So we're going to subtract x from both sides. We end up with negative x plus y on the left side. And then the x's disappear on the right. We've eliminated it from the right side of the equation. And this is equal to negative 11. We can leave it in this form, or we can multiply everything by negative 1 so that we don't have a negative 1 for our coefficient in front of x. And that would give us x minus y equal to positive 11. So all these signs just flipped. But I'll go ahead and stick with this first equation. So now we have negative x plus y equal to negative 11, and x plus y equal to 9. For this example, we're still able to skip step 2, and that's what we're going to discuss today. But for this example, it's not needed. So let's add the two equations, creating one equation with one variable. So step 2 is not needed because when I add these two equations, one of the variables will disappear. It will be eliminated. Negative x plus x is 0x plus 2y equal to negative 2. So we have eliminated the x variable. And then solving for y, we end up with y equal to negative 1. So we've solved this new equation, and then we're going to find the value of the other variable by substitution. So we'll substitute y equal to negative 1 into either of these two original equations. Now I'll go ahead and use this second equation. So we have x plus, so instead of y, we have negative 1 equal to 9. This is x minus 1 equal to 9. Adding 1 to both sides, we get x equal to 10. So the solution is the ordered pair 10, negative 1. So we want to check our answer, make sure that that is a valid solution to each of these equations. So for y equal to x minus 11, we have negative 1 equal to 10 minus 11. Negative 1 equal to negative 1. That's true. And then with x plus y equal to 9, we have 10 plus a negative 1 equal to 9. 9 equal to 9. That's also a true statement. So for this example, step 2 was not needed because when we added the two equations without doing any modification to either of these equations, one variable was eliminated. So let's take a look at step 2. So at step 2, as needed, we're going to multiply all terms in one equation by a constant. And, again, as needed, multiply all terms in the other equation by another constant. So that when the two equations are added, again, a variable is eliminated. The other 4 steps remain the same. And as always, when you're done, check your answer. Let's take a look at this problem. So we're going to solve the following system by elimination. We have the equation 2x plus y equal to 5, and the equation 3x minus 2y equal to negative 3. And when we're solving by elimination, the first step is to write both equations in standard form. And both equations are in standard form. Let's skip step 2 for right now. And we're going to jump to adding the two equations. Let's see what happens. So if we add these two equations, 2x plus 3x, that's 5x. Y minus 2y is negative y, equal to 2. Well, now we have one equation, but we still have two variables. And for solving, there's not much we can do when we have one equation and two variables. So adding these two equations right now did not eliminate a variable. But instead of having one y, if we had 2y, we would be able to eliminate this y variable when we added the two equations. But you can't just multiply one term by a value. You have to multiply both sides, every term in the equation, by that value. So what I'm going to do is I'm going to multiply all terms in the first equation by the constant 2. So we're going to multiply the left side by 2, and we're going to multiply the right side by 2. This results in 4x plus 2y equal to 10. These are equivalent equations. And then I'm going to add the second equation to it. So now when I add these two together, 4x plus 3x, that's 7x. 2y minus 2y, that's 0y, equal to 7. So now we have 7x equal to 7. We've added the two equations, and we now have one equation with one variable. We have 7x equal to 7. We're going to solve this equation. So we're going to divide both sides by 7, and we get x equal to 1. And then we'll find the value of the other variable by substitution. And I'll go back to one of these original equations to do this. Let's go to this first equation where we had 2x plus y equal to 5. So now we're going to have 2 times 1, because x is 1, plus y equal to 5. 2 plus y equal to 5. Subtracting 2 from both sides. This gives us y equal to 3. The solution is the ordered pair 1, 3. Let's check our answer. So we have 2 times 1 plus 3 equal to 5. So 2 plus 3 equal to 5. 5 equal to 5 works for the first equation. And then 3 times 1 minus 2 times 3 equal to negative 3. This is 3 minus 6 equal to negative 3. Negative 3 equal to negative 3. That's also true. So we've checked our answer, and the solution to this system of equation is the ordered pair 1, 3. So as a reminder, if we graph these equations, these two lines, they're going to cross at one point. Now, one point, well, that's the point they have in common, and that's the solution to this system. So why were we able to multiply both sides of this equation by the number 2? We used the multiplication property of equality. So when we multiply both sides of an equation by the same number, we keep the equality. So for any real numbers, a, b, and c, if a is equal to b, then a times c is equal to b times c, as long as c is not equal to 0. Now, if c is equal to 0, we do end up with 0 equal to 0. So this is a true statement. But we don't really get any useful information from this. And we also lose any of the meaningful information we had with A equal to B. And it's not going to help us solve the problem. So let's take a look at this in action. So if we have 2 plus 5 equal to 7, and we multiply both sides by 4, well, following PEMDAS, we'll do what's in parentheses first. We end up with 7 times 4. The other side is still 7 times 4. We have 28 equal to 28. We maintain the equation's equality. We also use this when we're solving equations. So if we had the equation x over 3 equal to 5, or 1/3 x equal to 5, we wanted to solve for x. Well, to undo this division, we would multiply by 3. But what we do to one side, we have to do to the other. That maintains equality. We end up with x equal to 15. So when we multiplied this first equation by 2, we were allowed to do this because of the multiplication property of equality. And then we created equivalent equations. That 2x plus y equal to 5 is equivalent to 4x plus 2y equal to 10. And this allowed us to solve this system of equations. Let's practice one more. So solve the following system of linear equations by elimination. We have 7x minus 5y equal to 15, and 2x equal to y plus 3. Looking at these steps, the first step is to write both equations in standard form. So the first equation is in standard form, but the second is not. So let's rewrite this second equation in standard form. So we have 2x equal to y plus 3. I'll subtract y from both sides. We now have 2x minus y equal to 3. So I'm going to go ahead and rewrite both equations. We have 7x minus 5y equal to 15. And then 2x minus y equal to 3. So what can we multiply either of these two equations by so that when we add them, one of the variables will disappear, will be eliminated? Now, writing both equations in standard form, really this is not a requirement for solving this. But when we have things lined up nicely like this, it may make it easier to see that if we multiply this second equation by -5, our y variable will be eliminated. So when I'm solving systems of linear equations using this elimination method, and I want to modify an equation, I want to create an equivalent equation, I draw an arrow, and then I indicate what I'm going to do. And what I'm going to do is I'm going to multiply this equation by -5. This is just how I show what I'm going to do. This is not any official math language that I'm producing here. So I'm multiplying the second equation by -5. That means I'm going to have negative 10x plus 5y equal to negative 15. I multiplied all three terms by -5. I'm not going to do anything to this first equation, so I'm just going to bring it over. 7x minus 5y equal to 15. So now we're going to add these two. 7x minus 10x, that's negative 3x. Negative 5y plus 5y, that's 0y. And then 15 minus 15, that's also 0. So we now have negative 3x equal to 0. Dividing both sides by -3, we have x equal to 0. Now we need to find the other variable using substitution. Going back to our original equations, you can pick either one. So I'm going to go ahead and pick this second equation, but it doesn't matter which one you choose. I will rewrite that equation. We have 2x equal to y plus 3. So where there is an x, we'll replace it with a 0. So 2 times 0 equal to y plus 3. 0 equal to y plus 3. And then subtracting 3 from both sides, we end up with negative 3 equal to y. And then we can rewrite this as y equal to negative 3. So the solution is the ordered pair 0, negative 3. So our solution is on the y-axis. Let's go ahead and check this really quick. So we have 7 times 0 minus 5 times negative 3 equal to 15. Well, this is 0 plus 15 equal to 15. And 15 is equal to 15, so that works. And then for that second equation, we have 2 times 0 equal to negative 3 plus 3. 2 times 0 is 0. Negative 3 plus 3 is 0, so that's also true. A great way to learn is practice on your own. We will discuss in a bit, but go ahead and pause your screen and do these two problems. So for this first equation, we have 7x plus 2y equal to 24 and 8x plus 2y equal to 30. So we have a positive 2y in both equations. So if we multiply either of these equations by negative 1, we'll be able to eliminate the y variable. I went ahead and multiplied the second equation by negative 1. And again, this is how I write what I'm doing. This indicates I'm multiplying the equation by negative 1. But this is just how I write it. You can kind of come up with your own system to show what you're doing. So when we multiply by negative 1, we end up with negative 8x minus 2y equal to negative 30. The important part now is when we add these, we're able to eliminate this y variable. We end up with the equation negative x equal to negative 6. Solving that equation, we get x equal to 6. Plugging this value into either of these equations, I did select the second one. And then solving for y, we get y equal to negative 9. So the solution is the ordered pair 6, negative 9. For this second equation, we have 9x minus 5y equal to negative 16 and negative 3x plus 7y equal to negative 16. I chose to eliminate the x variable by multiplying the second equation by 3. This produces this equivalent equation, this negative 9x plus 21y equal to negative 48. Adding these two equations, our x variable disappears, and we end up with 16y equal to negative 64. Solving this, we get y equal to negative 4. And then substituting this value into either of these equations. In this example, I chose the first equation. And solving for x, we get x equal to negative 4. So our solution is an x value of negative 4 and a y value of negative 4. Drop any questions you have in the comments. Continue practicing solving systems of linear equations using the elimination method, and I'll see you in the next video.